Black holes are not completely black. In the context of pure general relativity, without any additional modifications or considerations of other physical theories, black holes persist forever. Once a black hole arises, it will exist indefinitely. In the 1970s, Stephen Hawking utilized quantum physics to investigate the phenomena occurring close to the edge of a black hole, referred to as the event horizon. He discovered an unusual interaction between the quantum forces in our world and the one-way barrier of the event horizon that created a means for energy to exit the black hole. Hawking radiation can be defined as a slow but continuous flow of radiation and particles. As energy departs, the black hole loses mass and eventually disappears completely. Hawking radiation's emergence has led to the creation of the black hole information conundrum, where all the information about material entering a black hole passes the event horizon and is permanently lost. However, Hawking radiation does not contain any information, but it causes the black hole to finally vanish.
But then what happens when the black hole evaporates? What happens when the black hole evaporates is that the film evaporates, molecule by molecule or photon by photon. The outer boundary of the system just decays and gives off photons and eventually disappears. Where is the information that fell into the system? It's in the radiation which went out, which carried away the information that was on the surface. What happened to the image on the interior? Well, there's just no hologram left. It just disappears, it's gone. But that's not a violation of the idea that, that information is conserved. Where did it go? It went back out into the surrounding environment. That was the idea of a black hole as a hologram. A little bit later, through the work of Gerard 't Hooft and other people, and Juan Maldacena, myself a little bit, it was understood that not only a black hole, but the whole world or region of space of the whole world could be understood as a hologram. The idea was that if a region of space has a maximum entropy, a maximum amount of hidden information, and a black hole is the maximum amount of information that can be stored in a region of space, then it must be that you can describe that region of space by a system a quantum system whose numbers of degrees of freedom is proportional to the area of the region. A region of space can be described by a quantum system on the boundary with an area's worth of degrees of freedom. That was the idea of the holographic principle. Whole worlds, if we surround them by a mathematical surface, can be represented by a quantum theory, which is like the holographic film, whereas the region that they're describing is like the image of the hologram. We have these two sides to things: a quantum description, which is stored on the hologram, and a gravitational system. By gravitational system, I mean systems which contain gravity, maybe also quantum mechanics, and are what we all ordinarily think of as the reality, that they are represented as a kind of image of a hologram. This idea, which was a nutty idea at first, it wasn't taken seriously by too many people, eventually, largely through the work of Juan Maldacena, became a main staple of current physics. It is not only widely accepted, it's the basis for almost everything that's taking place in the area of the connection between quantum mechanics and gravity.
Stephen Hawking was interested in determining the fate of pairs of particles, such as a particle and its antiparticle, that emerge spontaneously in the vicinity of a black hole's event horizon. When a particle encounters its antiparticle, they annihilate one other almost instantly, without the universe at large being aware of their existence. Hawking demonstrated that if one of the partners crossed the event horizon, it would be pulled into the black hole while its counterpart on the opposite side of the horizon would be ejected at a high velocity. In order to preserve the overall energy of the black hole and adhere to the fundamental principles of physics, the infalling particle must possess negative energy, and hence negative mass, while the fleeing particle must possess positive energy. In this way, black holes release Hawking radiation, a form of energy that depletes them over time, leading to their evaporation. Stephen Hawking proposed that around the event horizon, pairs of particles are created and destroyed due to a combination of quantum physics and Einstein's theory of gravity. Sometimes a particle is absorbed by the black hole, allowing the other particle to be released as radiation. Hawking proposed that this process will ultimately lead to the evaporation of black holes. Recent theoretical research has confirmed Stephen Hawking's assertions regarding black holes, albeit with some nuances. Black holes would eventually evaporate due to Hawking radiation, with the event horizon being less critical than previously thought. Gravity and space-time curvature both contribute to the generation of this radiation. This implies that all massive entities in the cosmos, such as stellar remnants, will ultimately dissipate. Furthermore, the scientists utilized equations from the Schwinger effect, a related phenomena that explains the separation of charged particles and antiparticles when they appear from the vacuum in the presence of a strong electromagnetic field. The process is similar to particle pairs being influenced by intense gravitational forces around a black hole's event horizon. The researchers' mathematical analysis demonstrated the impact of any object with mass, not limited to super heavy ones like black holes, on pairs of particles and antiparticles originating from space's vacuum. These particles can be conceptualized as having a probability cloud that determines their potential locations in space, like waves, without other forces acting upon them such as electromagnetic or gravitational forces. The clouds of both the particle and the antiparticle will merge and undergo annihilation. If gravity or another force pulls more on one cloud than the other, they will be somewhat displaced. They will not intersect, therefore preventing annihilation, and they will emit radiation similar to a particle ejected from a black hole's event horizon. This hypothesis proposes that any item in the universe with gravity will emit Hawking-like radiation and eventually disappear. The mathematics suggest that this process will need an immense amount of time. However, the enduring remains of deceased stars like white dwarfs and neutron stars, which possess significant mass, could have their lifespans reduced if the event is genuine. But other experts disagree. For example, the theoretical physicist Sabine Hossenfelder of the Munich Center for Mathematical Philosophy thinks that a more careful examination could prove that the particle-antiparticle pairs don't genuinely emanate from huge things other than black holes. Current technology lacks the sensitivity to detect this evaporative effect and validate the new claim. Additional tests could concentrate on observing the Schwinger effect, which is still theoretical, to potentially strengthen these assertions. According to quantum field theory, virtual particles that arise and disappear permanently fill the physical vacuum. It is conceivable for the particle total energy to appear positive while the antiparticle total energy appears negative. The particle can escape to infinity, while the antiparticle can only lose weight and energy as it descends into the black hole. The particle appears to a distant viewer to be the black hole's Hawking radiation. Such a result seems to go against the unitarity and reversibility of quantum mechanics, which state that information cannot be lost. Based on quantum gravity theory, we could anticipate the same outcome. The second criticism is predicated on the idea of a frozen star. In fact, an observer at infinity will never experience the entire black hole's information loss, since they will never be able to see any portion of the shell beyond the event horizon. We refer to this as a frozen star. In this situation, the corresponding pre-Hawking radiation of the frozen star in semi-classical theory is coherent and can include information. Because discrete states occur in semi-classical theories, where general relativity theory describes space and quantum field theory describes matter, entropy, and temperature acquire finite non-zero values. As black holes evaporate, they decrease in size, and their event horizons approach the center singularities. As black holes approach the end of their existence, their gravitational pull intensifies, and their size decreases to a point where our existing understanding is insufficient to characterize them accurately. If we can improve our understanding of gravity, we can utilize the concluding stages of Hawking radiation to evaluate the theory's performance. Several contenders exist for a quantum theory of gravity, with string theory being the most advanced. While solutions to string theory remain elusive, it is feasible to leverage our understanding of the theory's overarching characteristics to develop altered iterations of general relativity. Under certain circumstances, the evaporation of a black hole can result in the formation of a tiny remnant, depending on the specific characteristics of the theory and the black hole's history. This nugget does not possess an event horizon, allowing a spaceship to approach and retrieve it. The nugget would be quite unusual, but would preserve all the information from the original black hole, thus resolving the paradox. The black hole may attain its minimal mass and lose its event horizon while retaining a singularity. Naked singularities, which are seemingly prohibited in standard general relativity, could serve as direct gateways to the domain of quantum gravity if they are real.